чем вчерашний, хотя вчера вот произвел впечатление, да, доклад ГУ, потому что у них такая, конечно, аппаратура, молодежи много. Молодежи много.
Он сегодня придет еще?
Он здесь. Может, с ним поговорить. Вот. У молодежи много. И с ними сейчас работают японцы и американцы. Вот к ним туда приезжает, и вот этот вот японец, которого там в середине фотографии был, он рассказывал про него. Поэтому вот нам надо тоже там закрепляться. Как-то. Ну такая аппаратура. Делать эксперименты у них надо. Такая аппаратура. Как-то надо это. Today very interesting talk about modern stress data for very high intensity seismic province Yunnan and Sichuan was performed by Dr. Wang. I know Dr. Wang near 10 years, and she used my program for analysis stresses, and I think it will be interesting for you too.
Thank you. Good morning. Thanks for Professor Vasky to invite us and give us a chance to communicate our research. My topic is background stress data before the Wenchuan earthquake and the dynamics of the Wenchuan thrust belt. As we know, using an algorithm called this, we can reconstruct the stress state based on focal mechanisms. The algorithm is developed by Professor Vasky. This method determines stress tensor. It can give us quantitative stress values. The results of the application using data show the background stress state around the Wenchuan belt because the Wenchuan earthquake happened in May 2008, and the data we collected from 1989 to April 2008. So we can get the background stress state before the earthquake. This figure shows the GPS distribution in China. From this map, we can see about three features. One, the movement velocity from south to north, and it decreases. This area it is maybe 40 millimeters per year, but in the north it is very small. The second feature is the velocity direction turn to the east from this direction to this direction. The Wenchuan area is in here, and the Wenchuan earthquake is here. Across the third feature is across the Wenchuan, the velocity decreases to almost zero. Okay. Across the Wenchuan, the velocity from maybe
because I changed direction.
Yes. The magnitude it decreases. So the collision between the India plate, we can see the collision between the India plate and the Eurasian plate controls the deformation and dynamics of the Tibet and its surrounding region, like this area and this area. Next. This figure shows topographic profiles. Across the Wenchuan this is the location of the Longshan, and between about 50 kilometers, the topography from the 4 kilometers to almost 0.
Is this red line? It is along Minshan?
Yes.
Fault.
Yes. Yes.
Along.
Not along. Cross. Yes. So it is very deep of the Longshan. This is the gravity data. The gravity data shows a huge change across the Longshan. This is a model of Clark and Royden. He thinks that the crust thickening beneath the east plate occurred without large-scale shortening, and it is caused by ductile thickening of the deep crust in a weak layer. That means under the crust of the Tibet, the low viscosity of the material moved toward the east, and here is the Sichuan Plateau. It is very strong, and the crustal flow moved here and is persuaded by the Sichuan Plateau, and piled piled here, and some material will move toward north or toward the south.
Around this basin.
Yes. And some material will pile here and will uplift the Longshan. Okay. This will cause the steep uplifting of the Longshan and cause the topography profiles. This is the Wenchuan earthquake and its aftershocks. Aftershocks. The crack reaches more than 250 kilometers. Geologists from geologists' survey, they tell us that the distribution of the aftershocks is very different from classical low-angle thrust force. In classical low-angle thrust force, the earthquake distribution will very wide, but this distribution is not wide. It is very shallow. So they say that the presence of steep mountain front and an absence of large magnitude low angle thrust force is very unusual. This is the deep structure of the Wenchuan earthquake. We can see that the fault is very deep, very. The angle is very high, but Anderson's classical thrust force is maybe 30 degrees. So the dynamics of the Wenchuan earthquake is mysterious. So from the above research, I can conclude a simple model like this. under the eastern Tibet is a viscous lower crust, and it's a flow from west to east. Here is the strong plasma, and the crust flow is persuaded here, and it will pile up under the Longshan. The uplifting will cause the Longshan the vertical uplift. So we can infer that the uplifting of the piling crust flow can make the stress intensity weaken. It is my guess. Next, I will do some research to this is the data from 1983 and then 89 to before the winter earthquake. Maybe 1,000 data. Nearly. It is the recent stress result. From this figure, we can see that the maximum stress axis coincide with geodynamics. And
This is maximum compression.
This is maximum compression. This is the stress intensity. You can see that characteristic of the stress orientation reveals that the Longshan region is under the eastward extrusion of the Tibet plateau, from this direction to this direction.
This is geodynamic type of stress data. Yes, this one.
This one as horizontal extension, horizontal
shear,
horizontal compression.
Horizontal extension, right?
This is compression. Compression, yes.
Horizontal compression.
Yes.
Very interesting, this figure.
This figure shows that weak stress intensity under the Longshan compared with other areas. Okay.
And very high on the start of the earthquake, yes?
Yes, the earthquake is here.
The start of earthquake.
The start is here. Here. So this can using our model to do some work to improve this conclusion. This is some kind of geology model. From this model, it tells us that the stress intensity increase linearly in ductile layer. This is ductile layer. This is a frictional layer. Yes. It will decrease along the depth. But this is aftershocks focal mechanisms like this. It contains more than 1,000 data. 1,000, yes. From the distribution of the depths, we can see that 20 kilometers, above 20 kilometers, it is a frictional layer. So I divided the data in several groups, from 5 kilometers to 10 kilometers, 10 kilometers to 15, three groups, and do their and reconstruct their stress state using these three groups. from this figure, we can see that in shallow layer, it is a low stress level. It is the 10 to 15 kilometer. You can see the stress level is high. But in 15 to 20 kilometer, the stress level don't increase linearly with depth. This is the quantitative average stress using this data. I figured using this coordinate, it is
Along the fault.
along the latitude. This is the average magnitude. In shallow layer, it is about 4 here. But in 10 to 15 kilometer, it is reached 8, maybe here.
Intensity of stress from red to green, but the blue, it is blue.
Blue is high. So from this layer to this layer, it increases with depth, but in deeper layer, it don't increase. It may be comparative with this layer. So so I want to use model to give the reason. This is the geophysical survey. So from this survey, we can get some necessary parameters in model. This is Wenchuan fault in east part. In west part, it is a lower velocity layer.
It is east. The left it is east.
This is
okay.
west.
West.
This is east.
West.
This is Sichuan. This is the
Eastern
Tibet. Eastern Tibet. So in my model, I give some parameters. This is the elastic. This is the Wenchuan here. This is the Eastern Tibet. This is the Sichuan Plateau. Sorry, here. Okay. These two layers, viscoelastic layer. After 30 millimeter years gravity isostasy, then push from west to east. It is the result. Next, I will give the enlarged area. This is the enlarged area. Okay. This is the lithostatic stress state. We can see that from shallow to depth, the stress increases with depth linearly. Then after eastwards pushing from the Tibet, the stress state changes very much. The stress intensity will enlarge in front of the Wenchuan, and when the uplift of the upper crust will decrease the stress here. Okay. So the distribution of stress along the depths of under the Wenchuan change. It did not along the model, the geology model. This model. Across the flow under the brittle layer will change the stress distribution along the depths under the Longmenshan, and the pile up and uplifting of the lower crust in front of the Longmenshan will cause the weak intensity, just like this. It is caused by the uplift of the weak crust. So.
Is stress changed from blue to red?
Red is high, blue is weak. Yes. I did not put the color from here. So this is the result. A comparatively weak stress level of the upper crust under the Longmenshan belt is the dynamics of this region. Model results, my model, show that uplifting of the piling lower crust below cause the weak stress intensity of this belt and cause the feature of the stress distribution along the depths. Okay, just like this. Okay, thanks for your attention.
Thank you very much.
Ну, в принципе, все ясно было рассказано, но если есть какие-то вопросы.
But maybe what this one. This is stress intensity.
Stress intensity.
It is like maximum shear stress, yes?
It's one misses stress. Yes.
Like
yes.
Yes. I think that it is elastoviscosity model. It is not elastoplastic. It is elastoviscosity model, yes? Elastoviscosity. Because
the middle and the lower is viscoelastic and
viscoelastic.
Yes.
Viscoelastic and elastic. I think that you show not only stress intensity distribution in your model, but and distribution of pressure.
Pressure, yes.
Because when you say that the stresses on the along Wenchuan fault weak, it means that along Wenchuan weak also compression, because for brittle destruction, this parameter pressure and shear stress connect by Coulomb-Moore diagram. You know about this, yes?
Yes.
And if you show distribution of stress intensity, please show distribution of pressure, because if for this zone stress intensity decrease, for this zone you should see and that pressure decrease too, because it means that this zone very dangerous for brittle destruction if the pressure decrease too.
Yes.
Понятно, да? То есть вот когда говорят, когда показывают уменьшение интенсивности сдвигаемых напряжений на будущем землетрясении, это может вызывать отрыв, потому что привыкли говорить о том, что повышается напряжение. Но надо понимать, что одновременно здесь снижается и давление. А хрупкое разрушение, оно как раз происходит чаще, именно когда слабое давление, или там не должно быть в этом случае сильного касательного напряжения.
При двух такой силовой модели это вот очевидно.
Да.
Мы снимаем одно боковое напряжение, проскакивает.
Да. Вот. Поэтому I think you in your presentation we should draft and distribution of pressure.
Yes.
And maybe show give the diagram more
Yes.
and connect between pressure and
Yes.
but very Еще есть вопросы?
Все очень интересно.
Что-то я еще хотел спросить. Ну, уже ладно. Есть еще вопросы?
Да нет, все понятно, очень интересно.
Спасибо, very nice. Ну, мы можем
Какое-то время они у тебя еще...
Да, можно вот поспрашивать, кто хотел. Профессор Гу, this man and this man want to ask you about your talk. Thank you.
Thank you.